Up until now, we've been working on dynamics. This includes moving objects, things like bullets firing, cannonballs flying, jumping off a cliff and seeing how long it takes you to hit the ground, such and such. Now we're moving on to the exciting realm of statics. This includes things that don't move, things like boards, doors, tables, stuff like that. The key point in statics is static equilibrium. This is when everything is standing still. Technically, this is when the net of all forces is equal to 0 and the net of all torque is equal to 0. Thus, no force in any one direction, no torque in any one direction, no movement or spin in any one direction. Okay, let's consider the table example. You're a mischievous child and you want to see how close to the edge of the table you can sit without tipping it over. Well, what forces do we have to consider? Of course, there's your force on the edge of the table, your mass times gravity, and we have the force at the table itself, its center of mass times gravity. We have two normal forces on each leg preventing the table from falling to the ground. But now if we look at the point just before it's tipping over, how's it going to be pivoting? Well, it's going to be turning clockwise because you're on the right side and it'll be tipping that way, and it'll be tipping around that leg, which means there's not going to be any normal force on the farther leg. It's about to lift off the ground, so it's not pushing down at all. Now how do you calculate torque? Torque is a lever arm times a force. The lever arm is the distance from your pivot point to the force, and it's always perpendicular. So there, I've drawn the lever arm. We know the force, still the mass of the table times gravity, so we can easily figure out the torque caused by the table by multiplying that force by that lever arm, which, for example, we'll say is 0.6 meters. We do the same thing with you, and we'll use x here for your distance from the point of rotation, or your lever arm. Now we can just set the torques equal to each other, because we know this is right at the point where it's about to tip. The mass of the table is perfectly countering you. If you move any closer to the edge, it'll fall over. But right now, it's all balanced. It's in equilibrium. If you think about it, it's a pretty cool place to be. For our last example, we'll consider a door. Now this door has a doorknob, a center of mass, and two hinges. The doorknob has no effect whatsoever, so we'll ignore it. I'll draw it anyways, though. The hinges are the only two places of contact this door has with the outside world. It's not touching the door frame, it's not touching the ground or anything else. So, what are the forces on these hinges? We can see there's got to be some upward forces, otherwise the door would just start moving downwards. We'll also assume that the upward forces on the hinges are split evenly between the two. But this can't be all the forces. If that were the case, the door would start to spin in a counterclockwise direction because there's all these upward forces on the right side. We know that's not the case. So there must be some torques acting on the system. Let's take the bottom hinge to be our center of rotation. Finding the torque caused by the center of mass is not too difficult. The lever arm is simply half the width of the door, and the force is simply the mass of the door times gravity. Now let's pause to look at the direction of torque. We use the right-hand rule to find this out. You curl your fingers in the direction that the torque would be going, so like that. My thumb is pointing upwards, so this is a positive torque. Now here, to counterbalance that, to arrive at a net torque of 0, we're going to need a negative torque. So you point your thumb downwards, and you see the force is pointing in that direction. Cool. Now the torque here, again, remember, perpendicular from the center of rotation, so the lever arm is simply the height of the door, minus a little bit on top and bottom we'll ignore, and the force. Here I'm going to strangely label the force in the y direction. Let's assume that I meant to label it in the x direction. Of course, it doesn't really matter, you can switch x and y as you want, but really I did this in probably the most confusing way possible. But we're going to stick with it for now. So the y direction is what you would think of as x and x is y. Either way, this is the negative torque as we found by the rule of thumb. Now our two torques have to add to 0, so we'll go over to the left side of the paper here and add them up. We'll see that we can easily define the force in this direction in terms of the mass of the door, the width of the door, the height of the door, and gravity, which we can all assume in the problem are given, so we can find that force. But now we see, if these are all of our forces, the door is going to start slowly moving to the right for some reason. But again, doors don't do this, so there must be some torque we're missing, some force we're missing. This is going to be a torque on the bottom hinge that we couldn't see because the lever arm was 0 because we were looking at that point. So now we'll have to go look at a different point. Let's call the top hinge our pivot point now, and recalculate the torques. The center of mass is going to be the same, which you can check very easily. And we'll also find out that the torque on the bottom hinge is going to be the same as the torque on the top hinge. This makes sense. The door is symmetric, so it wouldn't make any sense for the two to be different, except for they're in opposite directions, which is what prevents the door from spinning in circles or moving in one direction over the other. Now we just play with the algebra a little bit to prove all this, which is quite reasonable. We see the forces are equal and opposite, which is what means that all the forces add up to 0, all the torques add up to 0, and our static equilibrium is satisfied. You'll notice here at the end I eventually realized that my y and x were backwards and started to attempt to rewrite the equations before realizing how deep my mistake actually went. Bear in mind though, y and x does not actually matter. We define these however we want. We can define y to be in the sideways direction and x in the upwards direction. This is actually a lesson that I intended to give. Sort of.